When we're dealing with the conservation of momentum, one of the things that we need to look at are external versus internal forces and how they affect the system that we are working within. And in this frame of reference is what we'll call it. We'll say that external forces come from the outside of the system of particles whose momentum is being considered. And those external forces can change the momentum of the system. For example, if I have a gentleman on a sailboat, and so here he is on the sailboat, here's the sail. If he's sitting still in the sailboat, it's not moving at first, and the wind comes along and then pushes the sailboat and the man inside, then we say that this is an external force. So this force due to the wind is an external force, and it will change the momentum of the system. It'll go from 0 to the mass of both the man and the boat times the speed. Internal forces arise from the interaction of particles within the system. So let's say that it's a day where there's no wind. You have the gentleman, he's still inside the boat, that's a sailboat, and this time he takes a step forward. When he does that, if you remember in the last problem, the boat moves backwards, and because everything is inside, we don't change the momentum of the system. So here the momentum of the system started at 0 and it went to some number. Here it started at a particular number and then stayed at that particular number as we went on. That's the first part of internal and external forces. Let's look at a couple of examples. We have a club head, and that club head exerts an impulse on a golf ball. If we call the golf ball the system, we see that the rightward moving club head experiences a leftward force from the ball. The golf ball experiences a rightward force, then accelerates to the right because that's the net force. The forces have equal and opposite, equal magnitude, and they have an opposite direction. So the club head exerts an external impulsive force on the ball and changes the ball's momentum. So this is external, and then this is internal, or this is what we call the system. So the acceleration of the ball is greater because its mass is so small. We could say that if this is a gram and this is 100 grams, then we know that whatever speed this has, because this mass is so small, that should take off. Here we need to see that the initial momentum of the golf ball is not equal to the final momentum of the golf ball because we have an external force acting on that golf ball. In the next problem, or just this is an internal force in pool. I have 2 pool balls, and what happens is the 7 ball comes rushing in and hits the 8 ball. When it hits the 8 ball takes off in this direction, the 7 ball goes in the other. And because this is all within a system, then we say that the magnitude of their acceleration should be equal when they hit. So here we see that the initial and the final momentum are the same for this system, does not change. An explosion is just what you think it is. If you put a little bit of C4 inside of a car and then you ignite that C4, we have a object then that will just kind of come apart. The momentum is conserved in an explosion because all the forces are internal. There's no external force there. There's also an increase in kinetic energy in the explosion. This comes from the potential energy decrease due to the combustion of the chemical that's in the explosive itself. And we'll do a little bit more with explosions in an example problem or two. Guns and cannons, they have something called recoil. You'll see this in a lot of different problems. This means that the gun will move in a backwards direction while the projectile moves in a forward direction. And because the masses are so very different, the gun would be very massive, the bullet would be very small in mass. The speed of the recoil of the gun's really small, but the speed of the projectile is actually very high. In essence, that's a good conservation of momentum. This all is one system, and so when the gun recoils this way due to the exploding gases, the bullet ends up going in this direction at a very high rate of speed. And that's basically what recoil is and how it works. In the first example problem, I have a 5 kilogram projectile launcher. It shoots a 209 gram projectile at 350 meters per second. They want to know what is the recoil velocity. So here's my projectile launcher. It's just a tube. It's going to shoot out a projectile. So here's a bullet, and it's going out in this direction. We know that the bullet will move this way. We know that the launcher will actually have to move in the opposite direction. We want to know what is the velocity of this object. So this is the launcher. This would be the velocity of the bullet. The projectile launcher has a mass of 5 kilograms. The 209 grams, remember we need to convert this from grams to kilograms, so that'd be 0.209 kilograms. So this is 0.209 kilograms. Be very careful with your units when you're doing these problems. The projectile is moving at a speed of 350 meters per second. We'll say that's in the positive direction. So our speed for this object should be negative when we're done. We know the sum of the momentum before should be equal to the sum of the momentum, after, and it's because this is an enclosed system. The sum of the momentum before is 0 because nothing is moving, and after we would say we have the mass of the launcher times the velocity of the launcher plus the mass of the bullet times the velocity of the bullet itself. The mass of the launcher we know is 5. We don't know what the velocity of the launcher is. That's what we're trying to find. But the mass of the bullet is 0.209. And the velocity of the bullet is 350. If you go through and do your math, you'll find out that the velocity of the launcher should be negative 14.63 meters per second, which is far less than the 350, but still pretty significant. Notice that it is in the opposite direction as indicated by the negative sign. And at this point we're going to stop and go to an exploding projectile here in the next example problem.